Part 1. We left last week with the concept of a NAT, which we will quickly rediscuss today. We saw that a NAT is a network address translation box. A network address translator, or a NAT, is a box that does something which is, in principle, not allowed by the IP protocol, but is done, and consists in translating the local addresses that are typically said to be in the LAN side, local area side, into addresses that are accepted on the WAN side, in the global internet, and those are typically addresses given by the provider, which are on the public side of the NAT. The public side is usually called the WAN side versus the LAN side. And the trick, of course, you cannot translate many addresses to one unless you use an additional discriminating field, and the trick is to use as field the port number, which is practically always present, either in the form of a UDP port or a TCP port. And what this slide is illustrating is that it is possible that two different machines that have two different local addresses that were using the same UDP port number can communicate with the outside, but to the outside they will look like those machines that are the same because they have the same IP address but different port numbers. So the NAT will change the port numbers and will do it dynamically and will create and maintain this table on the fly. Now, on the fly means whenever the NAT sees a packet for the first time, for example, it sees this packet being sent to the outside, it will create the value on the right first time it sees a packet that matches this rule. Of course, doing that does not always work. It works if communication is originating from the local area side, from the private side of the NAT, towards the public side. Imagine you talk to a server. Now the server S is behind the NAT. Imagine you talk to a server on the internet. Normally, not always, but in most cases, communication is initiated by the client. In fact, that's in some sense a definition of a client. The server is there waiting, and the client is whoever initiates the communication. So if the communication starts from the local area side, then the NAT, when it sees the packet for the first time going to that server, can create an entry in its NAT table. And when the server will respond, the NAT will know to which machine and to which port number it should be sent to. However, if the server is itself behind the NAT, then we have a problem, because if the server is behind a NAT with a given address, then the server itself doesn't know under which address it's visible to the rest of the world. And it also doesn't know under which port number it's visible to the rest of the world. So if you put a web server at home in your local area network on port 80, and you will have an IP address which is the address that this server has on your local area network, of course it's a private address, so the rest of the world will not know how to connect to your web server. So it will not work just automatically. You will need to do something. Doing something is manipulating your NAT, so there is a whole folklore of terminology about the NAT. People say punching a hole through the NAT. If you view a NAT as a barrier, making an entry in the table is punching a hole. The entry is in principle done automatically, but if it's not possible, like in the case I mentioned, you need to do it manually. So typically you can log into your NAT, which is often your ADSL or Cablecom modem, and then you can write explicitly a table entry. This is what you need to do if you want to run a web server at home, for example. Very few people run web servers at home, and if you run a web server, it's something very static usually. But very many people run Skype, for example. If you do IP telephony, you have exactly the same problem. A is calling B, A and B are behind NAT. How can A call B? You don't know what is the IP address of B seen from A, even if you know the name of B. So you need a third party, typically, which is on the global internet. This is what Skype does. Skype solves this problem, and this was what made Skype work and be useful. This is why you need to go to at least one third party that will see A and B from their public, will see the public addresses and the port numbers that are used by the communication. If the NAT is a very good NAT, which is called cone or restricted NAT, this is a NAT that does this mapping the same for everybody. So when you talk to the server of Skype, you're visible as under a certain address with a certain way of mapping the port. And when you will talk to another Skype partner, this mapping will be the same. If that's the case, then the Skype server can only help you find what the mapping is. And once you know the mapping, A and B can communicate directly without going through Skype servers. In many cases, it doesn't work. The mapping is specific to a given source-destination pair. If that's the case, its communication is impossible without going through a third party which is connected to the internet, which is what often happens with Skype. You go through an intermediate system that relays all the traffic at the application layer. That is what happens when you hack the architecture. The TCP IP architecture says the transport and the application layer are end-to-end, and anything in between is IP or MAC, things below. If you violate the architecture somewhere, like you do with the NAT, then this principle might not work. So the global system might not work. So hacking something somewhere is just the beginning of a long chain of hacks which you will need to do to maintain the system operating. Quick question. When a NAT has a packet to forward and an association exists in the NAT table, what kind of matching does it do? Of course, it does an exact match and not the longest prefix match. Here, you need to match exactly the exact address and the port number, which essentially tells us a NAT will be difficult to do at the large scale. If you have a large company with 100,000 machines and you would like to hide them behind a NAT so that the rest of the world will not see exactly their addresses, then you will have to work hard on making a special NAT that will be able to look up the table for an exact match very, very fast. That exists, but it's fairly exotic. Most NATs are for the small scale. Question?
Would a limitation in that case be the port number? Since the port number can't be 100,000, would a NAT be able to serve 100,000 users behind the NAT?
So the question is, would the NAT be able to serve 100,000 users and have enough port numbers? With one single IP address, no. But what usually is done by company NATs, you have a block of IP addresses, not just one. So you get from Swisscom, for example, 256 addresses, and then you can map your 100,000 internal addresses to those 256 external addresses. This is what is sometimes done in those rare cases. But again, it's a hack. That's not a thing that's very desirable. It has lots of problems, as we have seen. Another question. From WAN to LAN. So the red arrow here is showing from LAN to WAN. So if we go the reverse direction, what does the NAT modify in the IP packets? In fact, in the transport level packet. I close the poll. And it changes only the destination port. From LAN to WAN, it modifies the source port and also the source destination address. And of course, in the reverse direction, it does exactly the opposite. So a LAN is something non-symmetric. A NAT is something non-symmetric. It has a LAN port and a WAN port. This is why sometimes when you buy a router at Migros or at Interdiscount, some routers are in fact NATs, and this is why they have what is called a LAN port and a wide area port. Voilà, that's all we'll discuss about NATs. We've seen masks already, so I recall what is the goal of mask. An IP address is always structured into network part and host part, and this is used in the IP forwarding algorithm. For example, when a router, ED2IN, which is this machine, has a packet to send, it has to know whether it has to send it directly or whether it should go to the routing table. For example, if it sends a packet to this address, 128.178.15.7, which is a machine that is on, it is this one, STI-SUN1, then this router knows, has to know whether that it is directly connected to it. And it has to know this. How does it know it? Then the IP theory says it should be done by analyzing the destination address and the mask. Which mask? The mask of the destination or the mask of me? Well, the answer is the mask of me. In fact, the masks of all my interfaces. This one has 3 interfaces. Each of them may have a different mask. What this machine has to do is take the destination address, this one, apply the mask of this interface, of that interface, and of that interface. If there is a match for any of the 3, then it means it's local to that interface. Local is one way of saying this. Another way, which we will very often find, is on-link. On-link means on this, in the same subnet or in the same local area network. And this is how it's illustrated on this modern version of a routing table. Of course, such a match should exist only once, because if the mask here applied to the destination address says yes here and yes there, that means that there are 2 subnetworks that have the same subnet part, which is physically possible. It's all done by configuration and software. You can do it, but it's in principle against the IP principle. So it means 2 subnets cannot have the same subnet part. As for NAT, you can start playing with violations and see what happens. The principle is that should not happen. In other words, one IP subnet must correspond to one network part. That's one of the weak parts of the Internet protocol, because the Internet protocol encapsulates how things are organized in its hierarchy by local information that can even be updated by users. So there are lots of ways things can go wrong because you have to put some configuration in machines that reflect how the network is. We will see in a minute that most of the time it's not done by users, but done by DHCP servers. And the reason for that is to avoid problems of this kind. This we've seen already. There is very often a confusion about masks, subnets, prefix, and what is called network classes. So this slide is completely obsolete. But I show it because you find it in lots of places. In the past, when I was young, the IP addresses were classified in class A, class B, class C, class D, or I say ABC essentially. And the idea was that the class A networks would be very large network, where the network part would be essentially 1 byte. The class B network would be smaller network, where the network part would be 16-bit. which is shown here, in fact, on this slide. And the class C network would be smaller networks, where the network part would be 24 bits. So the idea is if you have a network at home in a small enterprise, you take the mask to be 24 bits. If you're a larger company, you take the mask to be 16 bits. That was done in '94, for example. So at EPFL, the network part was 16 bits, which means it was as if the EPFL was like one big local area network. And the idea was that that would match the different network sizes that could occur. Very quickly, of course, people realized it's not a good idea. We need more flexibility. And also, typically, the subnet prefixes are usually much smaller. They are the masks are usually at least 24 bits. So this is completely obsolete, but many people continue to use it, so don't be fooled. Those are just labels on the address classes. In particular, the idea was that blocks of addresses would follow this hierarchy. If you had a class A block, you had exactly one block of address. For example, the IBM block is 9 dot something, the first byte equal to 9. But today, this is not true at all. You can have a block that is made of many pieces coming from class B or class C, for example. Now, a little question. Here is a network. Here I have local area networks, Ethernet cabling system, if you want. And there are devices, like this is a bridge or a router. Here are some addresses of machines, and the masks everywhere are 255, 255, 255. In other words, 24 bits. Is it possible that host A has this address? Yes or no? So for a test, that would be a hard question because the penalty for giving the wrong answer is high. No. Assuming all the other addresses are correct. Of course, if there are errors everywhere, the problem is unsolvable. Assume every address is correct, except perhaps A. Is that a valid choice for A? I close the poll. And the majority says no, which is correct. The majority is always right in Switzerland. The answer is no, this is not possible. Why? Well, because host A is on the same local area network as this interface. Because a bridge is a layer 2 device, so a bridge extends a local area network, but the two sides of a bridge are in the same local area network. From the viewpoint of IP, remember the goal of IP, the Internet protocol, is to interconnect things that are networks connected at the local area layer, which means at the MAC layer. So from the IP viewpoint, all of those things are in the same thing, in the same subnetwork. So this and that should have the same prefix, which is not okay because this is 78. So this is not correct. This should not be done. at least if you want to do things according to the principles. What should X be, a bridge or a router? It should be a router. If we believe in the numbers that are given, X is interconnected to local areas that have different subnets. So it cannot be a bridge. It should be a router. Last question of this module. I mentioned that at our sister school in Zurich, ETH, the subnet mask is 26 bits. So if you go for a visit to ETH and you want to configure your machine, which probably will be done automatically, but if it's not done automatically because you want to insert yourself into the Ethernet network, what mask will you need to put for IPv4? If you have a very modern operating system, it will ask you for a number, 26, you will put 26, but I haven't seen such a modern operating system yet. So it will ask you for a mask. I close the poll. And the mode of the distribution, which is also the majority, is the correct answer. This is an exercise in binary to decimal representation. The mask is this long string of bits. So the question is, so we see that it goes up to the last word. So the question is, what is this string of 8 bits in decimal? The first bit means 128. The second bit means 64. The others are 0, so it's 128 plus 64, which is 192. Admittedly, it's a bit awkward, but this is how it's done. So this is the subnet mask at ETH. Voilà, that's the end of this module. Without further ado, we move